Hey everyone, and welcome. Today, we are diving deep into a topic that can be a real game changer for your CUET score, Haloarenes. Now, I know this chapter can feel a little tricky, but trust me, it's a goldmine for marks if you know the concepts. And that's what we're going to do today. Make sure you walk away ready to grab every single point.
So let's just jump right in with a classic CUET-style question. Look at this. Why is chlorobenzene, our haloarene, so much less reactive, you could even say lazy, compared to its cousin, cyclohexyl chloride, when it comes to nucleophilic substitution? Give it a thought. We're going to unpack this completely by the time we're done.
So did you hesitate a bit? Maybe you weren't 100% sure. Well, that's perfectly okay. In fact, that's exactly why you're here. In the next few minutes, we're going to clear up all that confusion so you can tackle questions like this with total confidence.
And let's be real, this isn't just about learning cool chemistry concepts. This is about scoring marks. Getting a solid grip on haloarenes can literally add a guaranteed 5 marks, maybe more, to your chemistry paper. So stick with me and let's make sure those marks have your name on them. So why do the exam setters love this topic so much? Let's quickly break down why haloarenes are such a high-yield area. It's way more than just memorizing reactions. It's like a central hub for so many core ideas in organic chemistry.
Here's the inside scoop. The questions you'll get from haloarenes aren't just simple recall questions. They are conceptual MCQs designed to test your real understanding of things like resonance, inductive effects, and reaction mechanisms. And the best part? When you master this topic, you're not just learning about haloarenes, you're actually building a stronger foundation for chapters on benzene and other reaction mechanisms too. It's a win-win.
Okay, let's get right to the heart of it all. The entire story of haloarenes, why they're stable, how they react, all of it boils down to the special nature of that one bond, the carbon-halogen bond. And the secret ingredient? It's all about hybridization.
Now this is the most critical piece of information, so listen closely. In a haloarene, the halogen is attached directly to an sp2 hybridized carbon. I'm going to say it again, sp2 hybridized carbon. Please burn that phrase into your memory. It is the key that unlocks absolutely everything else we're about to discuss.
So what's the big deal about sp2 versus sp3? Well, check this out. In a haloalkane, you have an sp3 carbon. But in a haloarene, it's sp2. An sp2 orbital has more s character, about 33%. Now you can think of the s orbital as being closer to the nucleus, kind of like it's being held on a tighter leash. So more s character means the bond is shorter and much, much stronger. This is reason number 1 for their low reactivity.
But wait, it gets even better. You see those lone pairs of electrons on the halogen? They're not just sitting there doing nothing. They actually jump into the party. They participate in resonance with the whole benzene ring. And look what happens. That carbon-halogen bond is no longer just a single bond. It gets a partial double bond character. And we all know trying to break a double bond is way tougher than breaking a single one. This is reason number 2 for their incredible stability.
Okay, get ready, because we're about to tackle the biggest paradox of this chapter. This is a favorite area for examiners to ask questions, so lean in. Halogens are deactivating, but they are also ortho-para-directing. Now, how on earth can something slow down a reaction, but at the same time tell the new guy exactly where to go? It sounds totally contradictory, right? Let's break it down.
I want you to imagine a constant tug-of-war happening inside this molecule. On one side, you have the inductive effect, the negative I effect. Halogens are super electronegative, right? So they pull electron density away from the ring, kind of making it electron poor. This deactivates it. But on the other side, you have the resonance effect, the plus R effect. Here, the halogens' lone pairs are actually donated into the ring, which increases electron density, but only at very specific places, the ortho and para positions.
So who wins this epic tug-of-war? Well, when it comes to overall reactivity, the winner is clear, the inductive effect. It's the stronger force, and its pull is so powerful that it makes the whole ring less reactive than even plain old benzene. And that, my friends, is why we call halogens deactivating. But here's the really clever part. Even though the overall reaction is slower, the resonance effect acts like a GPS. It has already made the ortho and para positions rich with negative charge, basically putting up giant welcome signs for any incoming positive electrophile. So think of it this way. The minus I effect controls the speed of the reaction, but the plus R effect controls the direction of the attack. Okay, so let's circle all the way back to that first question I asked. We now know the CX bond is super strong. But there's actually more to the story of why nucleophilic substitution reactions like SN1 and SN2 are so incredibly difficult for haloarenes.
Here are the 4 massive walls a nucleophile has to break through. 1. That CX bond has partial double bond character. It's just too strong. 2. For an SN1 reaction, you'd have to form a phenyl carbocation, which is ridiculously unstable. No way. 3. For an SN2 reaction, the nucleophile can't do a backside attack because the big, bulky benzene ring is completely in the way. And 4. The haloarene molecule is already pretty happy and stable thanks to resonance, so it has very little motivation to react in the first place.
Phew, that was a lot of theory, I know. So how do we make sure all this actually sticks in your head when you're sitting in the exam hall? We need a quick way to recall this stuff. So here is a super simple trick to remember that big paradox we just talked about. I want you to say this out loud with me, or even better, write it down right now. Inductive is the in charge, but resonance provides the roadmap. Simple, right? The I in charge reminds you that the inductive effect is in charge of the overall reactivity. It deactivates. And the R in roadmap reminds you that resonance provides the map for the incoming group, directing it right to the ortho and para positions. All right, theory is done, memory trick is locked and loaded. It is time to switch from learning mode to exam mode. Let's put your knowledge to the test with some real CUET-style questions. You ready? Let's do this. Okay, question 1. A nice, simple, fundamental check. Go ahead, pause, and pick your answer. You got it? The correct answer is, of course, B, SP squared. Remember, this is the starting point for absolutely everything we've talked about. It's what makes that CX bond so special. Next up, a fill-in-the-blank for you. The CX bond in haloarenes gets a what kind of character because of resonance? The answer is partial double bond character. You have to know this exact phrase. It's the perfect explanation for the bond's strength and its unwillingness to break.
Time for a match the following. This is where we really see if you can connect all the dots. Take a second, pause, and match them up. Ready? Let's check our work. The I effect is responsible for the deactivating nature, so 1 goes with C. The plus R effect provides that ortho-para roadmap, so 2 goes with A. The big barrier for SN1 is the unstable phenyl cation, so 3 is B. And finally, the barrier for SN2 is that blocked backside attack, so 4 is D. How'd you do?
Fantastic practice, everyone. Now let's get serious for a minute, because knowing the right answers is one thing, but knowing how to avoid the wrong ones is just as important. We need to talk about the traps, the common mistakes that students just like you make on this topic every single year.
Please, I need your full attention here. Trap number 1. Never, ever think that haloarenes react just like haloalkanes. They are completely different beasts. 2. Don't forget that constant tug-of-war between the -I and plus R effects. 3. And this is a huge one. Deactivating does not always mean meta-directing. Halogens are the classic exception. 4. Never forget about resonance when you're deciding where the product will form. And 5. Do not mix up the super unstable phenyl carbocation with the super stable benzylic one. Watch out for these traps.
And that's a wrap on our deep dive into haloarenes. So, be honest, how did you do on those 3 practice questions? Let me know your score down in the comments, 1, 2, or a perfect 3 out of 3. If you nailed them, that's amazing. If you missed one, just go back and review that concept. If this explainer helped you feel more confident, make sure you hit that subscribe button to join our community of CUET achievers. Keep working hard, and I'll see you in the next one.